In this video we'll start looking at the DMA system that I'm going to be designing for the Z80 computer project. We'll be looking at this circuit here. This is part of the DMA system. The floppy drive interface consists of three main parts. We've got the floppy drive interface itself, which you've already seen. We've got a 16-bit counter which we don't need attached at the moment to test this circuit, and then we have the control circuit, which is what we have on these two breadboards. So if you're not familiar with DMA, I'll just quickly explain what it's for and what the advantages are in implementing it, because it's quite a lot of work to implement it into a system, but it's well worth it. And I'll just quickly explain what it is and why we're adding it to our system, and then we'll start demonstrating this circuit. So normally when a Z80 processor wants to transfer data, it typically does it in two phases. So the first phase, if we look at this diagram, very simple diagrams, oversimplified, but for argument's sake, let's say we have a device, so it might be our floppy drive system, and we have a value we want to transfer into RAM. So the first thing the Z80 does is it performs a read. It might be a memory read, or it might be an in-out read, and it supplies an address to the device, so the device can be selected within the system. Normally there are buffers etc between these, but I've ignored all those. I'm just really looking at the data flow, and as I say, the Z80 will provide the address for the device. The device then responds by outputting the data that we're trying to read, and the Z80 reads that data. So it now has the data that we're trying to transfer into RAM. The next phase of the transfer is the Z80 will perform another cycle. In this case it's a write cycle, and it will provide an address to the RAM. So that's where in RAM it's going to save or store the value, and then it will send the value through the data bus to RAM. So it's a two-step process. It's fairly inefficient, but also it requires the Z80 to be involved in the process. DMA, on the other hand, DMA stands for Direct Memory Access, and you'll see why it's called that. In DMA mode, the Z80 effectively releases control of the data bus and the address bus, so it goes into tri-state as far as the connection to these buses and several control lines is concerned, and then the device itself is responsible for providing the required address to RAM, and then it is also responsible for transferring the data through the data bus into the required RAM address. So you can see a very efficient single step process, and it seems like it's a no-brainer. Now, to make this work, you do have to add quite a lot of electronics and circuits to the design, but as you can hopefully see, it's worth the effort because it greatly speeds things up. So for example, a transfer like this is only going to take, in our system, less than a microsecond, whereas doing it like this takes maybe 20 or 30 microseconds per byte. So this is probably 25-30 times faster using DMA. Now if you're not intending to implement DMA, then it's best not to use in-out operations to access your device, simply because the Z80 automatically inserts wait states into the in-out instruction stream, so it tends to slow it down slightly. If you use mapped memory addressing instead, then it will of course save a few microseconds for each bus cycle, so it does save some time. I used in-out operations to access our devices because I was always intending to implement DMA, although having said that, I've already demonstrated that we can still use programmed in-out to access our floppy drive controller. The only disadvantage is that if we want to use double density formats for the disks, we have to run the board at 5 MHz, or the Z80 at 5 MHz, rather than 2.5, but that's not a big issue. But having said that, as I keep saying, I'm doing this project for fun, so I want to experiment and see how we can implement various features into it. So what we'll do now is look at what's required to make DMA actually work, and it's not horrendously complicated, but it is quite difficult to explain. So we'll look at the relevant page from the Z80 handbook that shows us how to get control of the address bus, the data bus and various control lines. So all we have to do is pull the bus request line going into the Z80 low, and we can do that at any point in any M cycle, and at the end of the current M cycle the Z80 in theory should put the address bus into tri-state mode, it should put the data bus into tri-state mode, and it should put the various control lines into tri-state mode, so they're all floating. The control lines it releases are memory request, read, write, in-out request and refresh. Now one important thing here is if you're intending to monopolize the address and data bus for any length of time, you will need to implement your own refresh counter and refresh cycle system, otherwise you'll start losing data from the DRAM. We're not going to worry about that because we're only using around 1 microsecond every 32 microseconds, so we're only using one complete cycle in every 32 or 33 cycles, so we don't need to worry about doing that. We will need to make sure that the other 4 lines are properly handled. We will be making use of memory request, read and write, because we'll be transferring data from and to RAM, and although we're using in-out to access the floppy drive controller chip, we're not using it during the actual DMA transfers. But we will need to make sure that the in-out request line is handled, otherwise if we leave it floating it could cause problems. So once the Z80 has released all the buses and control lines, it lowers the bus acknowledge line to inform our circuit that it now has access to those buses and control lines, and so that's what we make use of to determine when to start our transfer. Once we've got control of the the data bus, address bus and control lines, that's when things start to get a little bit more complicated, because we then have to effectively take control of the system with regard to accessing RAM and our device. So we effectively have to emulate the operation of the Z80. If we look at the read and write cycle of the Z80, again this is from the Z80 handbook, then there are 2 cycles here. We've got one for read, one for write, and we have to provide these same signals. Now these lines of course are already connected to the memory system, the decoder, etc. So we can make use of them because they've been released by the Z80, but we do need to make sure that we adhere to the same timing, because our memory circuits, decoder, everything else, the DRAM in particular, has specific timing requirements. We do need to make sure we adhere to that and do exactly the same thing that the Z80 would do, same sequence, same timing. So it looks a bit complicated. The other thing of course is these control lines that we'll be making use of, we have to release when we're not using the DMA system. That's when the Z80 has not granted us access to the data and address bus, so we have to use tri-state buffers between our DMA control system and the control lines, and the same with the address bus and the data bus. We can't just leave our system inactive. We need to make sure it's actually disconnected as far as trying to drive those circuits is concerned. So how do we go about providing these sequences of signals? Well, that's what this circuit does. So this circuit is relatively straightforward. It's not as you can see, it's not a horrendously complex circuit. Sorry you can't see it very well. I've got the logic analyzer attached to it, and we'll see what the logic analyzer makes of this in a few minutes. But as you can see from the diagram for the Z80, The Z80 performs all its functions in a series of T cycles. These are just main clock cycles, and this is the clock going into the Z80. We can ignore the instruction fetch part, that's the M1 cycle. We don't need to simulate or emulate that because we're not going to be fetching instructions, but we do need to provide this sequence of clock cycles and signals in this sequence and with this exact timing. So we need 3 full clock cycles, and then we will need at least another half clock cycle to kind of end the process and hand control back to the Z80. So the way we go about this, and I'll show us the circuit in our future video when we look more closely at the floppy drive interface, but the heart of this circuit is a series of 4 daisy-chained flip-flops, and they are fed from the main Z80 clock. So what will happen is when we feed the clock into the first flip-flop, assuming they're all reset into a common starting phase or point, then the signal will ripple through the 4 flip-flops, and I've used a flip-flop with complementary outputs. So for each phase we have both a high going signal and a low going signal, and that's exactly what we need to be able to make use of the clock phases. All we have to do then is for each output from the 4 flip-flops, we use those to control the relative timing. Now we can't use them directly for the most part, because as you can see, certain signals span multiple clock cycles, so we can't use the output of this, for example, because otherwise this signal would end at this point and it would just go back high again. And what we can do is use an external data selector so that the signals here select the various channels on the data selector, and assuming that the inputs to the data selector are set to high or low values, we can just feed those through to the output, and then the output will take on whatever form we want it to. And it will make more sense when you see the circuit, but I won't show it in this video, but I will come back in a future video and show that. But just for now I want to show this actually working. So I'll show it working using the LEDs to start with, and then we'll look at the logic analyzer. So what I have here is a signal generator connected to the clock input of the daisy chained flip-flops, and then the rest of the circuit is there just to provide these additional circuits. This circuit does several other things as well, because we still need to be able to access the floppy drive controller directly using in-out instructions, so we can actually load it. The DMA only takes over once the transfer from the floppy drive controller starts, but we still have to load up the parameters into the floppy drive controller beforehand to tell it what we want it to do. This also takes signals from the latch that you saw on the floppy drive interface to control the direction of the transfer, whether we're reading the floppy disk or writing to it. And it also incorporates a gate so that we can disable the DMA transfer and use programmed in-out if we want to continue using it in the way that you've seen it working already. It also controls the counter, so that's a 16-bit address counter, because we need to be able to load this using 2 in-out cycles, because we're loading it with 2 8-bit values, 16-bit counter of course, for the address bus. But these are 74 LS161s, and to load them we need to apply the required data values to the inputs. We need to assert the load pin on the pair of devices we want to load, but then we have to apply a clock cycle to the devices so that they'll accept the incoming data. So this circuit has to cater for all that, and it also has to generate the enable and clock cycle signals to the counter. So it does quite a lot. There's only a few ICs here, and in fact about half of these ICs won't be required as additional devices in the design when we go to the main PCB, because there are spare gates already available on the main PCB. So what we have on this board are the circuits to provide the signals we need, and then in addition on the right here we have the LEDs. So these LEDs, the top one is the read enable that goes to the floppy drive interface device. The next one down is the write enable, the next one down is the chip select. So these three are the lines going to the floppy drive controller, so that either the DMA can access it or that the Z80 can access it directly if we're using the in-out commands to program the floppy drive controller. The next one down, the red one, is the bus request line, or at least indicating the bus request status. The next one down is the enable output that controls the counter. The next one down is the clock that goes to the counter. And remember that each DMA cycle is only one transfer, it's only one bus cycle, and then it hands control back to the Z80, and it waits until the floppy drive interface tells it that the next byte is ready. So the way this works overall is the input to this that triggers it and starts working is the DRQ line from the floppy drive interface device. That goes high whenever the device has a byte waiting to either be written into the floppy disk if it wants more data, or if it has a byte ready to be read from its internal data register and sent through to RAM. So that's a DRQ line going high. It starts the bus cycle. So the first thing it does is it generates the bus request. So you'll see the red light come on, and then the circuit waits until the bus acknowledge line goes low from the Z80. So the Z80 will at some point give us access to the address and data buses, and it indicates that by lowering the bus acknowledge line. This circuit then will start using the incoming clock signal to go through the various steps required to generate these signals. So the signals going out are indicated down here on these four LEDs. So on the left we have the write. Now don't forget, these are the read and write going to the floppy drive controller device, and these are the read and write that go through to the Z80. So they're not the same thing. So we have the write signal on the left here, the read signal, the in-out. So although we're not using the in-out directly, we still have to control it to make sure it's not left floating. Otherwise we could end up with data going to the wrong part of the system when we try and write to RAM. And then we have the memory request line on the right. The two LEDs on the left here are the address 0 and address 1 lines that go through to the floppy drive controller. And again, we have to force those high when the DMA system comes into operation, because the data register in the floppy drive controller are at address 11. So these two LEDs should come on in DMA mode. So to simulate this, what I've got is this yellow jumper is connected to what would be the DRQ input. What I've done is connect the output of the bus request line to the input of the bus acknowledge line, so we don't need to mess about giving ourselves a bus acknowledge. So it will be automatic. As soon as the bus request line goes low, it will automatically start the process by giving us a bus acknowledge return. So all we have to do is take the input from the DRQ, send it high, and that will start the process running. This white jumper just sets the direction whether we're reading or writing. So I've got the clock set to 0.5 Hz, which should be slow enough for us to see what's going on. So we'll power this circuit up, turn on the signal generator. The only LED that's come on so far is the clock LED going through to the counter, which in this case it's gone high, but you should see that go low as part of the DMA cycle. So we'll start this running. We'll take the DRQ line high. So you can see the process is now running through. Don't worry if the signals don't make sense just yet. It should make more sense when we look at the logic analyzer. So it went through a cycle. Now in particular look at the top two here. So if we look, you'll notice that part way through the cycle the second LED down has come on, so that's the right enable line, and then we'll terminate the cycle. And if I change the direction, so we're now going to a read mode, we'll start it running again. This time notice the top LED comes on, so we can control the direction of the transfer. Okay, so the LEDs won't make that much sense. One other thing I'll just point out is the two LEDs down here. Notice that they both come on when the cycle starts, because we are forcing the floppy drive controller to give us access to the data register. Okay, so what I'll do now is move the camera so you can see the logic analyzer. I'll change the clock coming into maybe a hertz just to speed things up a little bit, and then we'll look at a couple of cycles and see if the cycles match what we need the system to do. So we have the logic analyzer set up with all the signals and control lines that we want to look at, and it's set to trigger when the bus request line goes low, and that's really the start of the DMA cycle. So what we'll do is we'll arm the analyzer. I'll move the DRQ jumper. We're in write mode here. It takes a few seconds, so the clock's only running at 1 hertz, and I'll stop the analyzer. And we've captured some data. So I've got this set to 1 second per division, and if we scroll across, we can see the data we've captured. We've got the clock at the top. We've got the DRQ line, that's the line that comes from the floppy drive controller. It goes high when there's data ready. This is a read cycle, by the way. And then we have a bus request that goes low, starts the process by asking the Z80 for control of the buses. The Z80 would normally provide this signal. There'd normally be a gap between this part of the cycle and when we get the bus acknowledge, but these are connected together, or at least it's inverted and then fed back into the circuit, so we don't have to mess about with jumpers every time. But if this bus request line wasn't fed back into bus acknowledge, then the circuit would sit there indefinitely waiting for the bus acknowledge to be asserted. But once the bus acknowledge is asserted, the cycle starts. Like I said, it's a read cycle, and if we compare the signals to what is in the data sheet, so what we should be getting is memory request and read should go low at the same time, and that should be the first falling edge of the first T cycle, and as you can see, that's exactly what's happening. Now it may look like the system isn't working correctly because we've got both a write and a read line going low, but remember that one part of the system is being read, so we're reading the floppy drive controller, and the other part of the system is being written. We're writing the value to RAM. The other signals, the chip enable line for the floppy drive controller is also going low for the entire cycle, which is what it should do. The count enable line going to the address counter towards the end of the cycle goes high, and the clock going to the counter also goes high at the same time, and that is to increment the counter. So for the next DMA cycle we'll be pointing at the next memory location. So all the signals seem to work. What I'll do is move the direction jumper on the DMA circuit, and we'll go through another cycle and see if it's switched to write mode. So we'll arm the analyzer, start the process by taking the DRQ line high, stop the analyzer. Okay, so we've captured a write cycle. So notice this time we're getting something that looks like the write cycle from the Z80 datasheet as opposed to the read cycle we saw the first time, and we've got this short write cycle or write line phase here. The memory request is still going low when it's supposed to, so you can see that this looks pretty much identical to what we're seeing in the Z80 datasheet because it's doing effectively the same thing. So once again you can see that one part of the system is performing a write and the other part is performing a read. So in this case we're transferring data in the opposite direction. So it's a fairly simple circuit, but it's doing quite a lot, and it's providing us all the control signals we need for the DMA system to work. There are still a few things to work out yet, how it's going to control the buffers on the data line, etc. But fundamentally all the things we need are here. It's already got the capability built in to allow the Z80 manual access through the in-out ports to the floppy drive controller device, and it's also got the ability to provide the required clock pulse to the counter when we want to load a value into it. So it has all the requirements to give us full control of the floppy drive interface. We just now need to integrate this with the counter and then with the floppy drive circuit itself. So we'll do that in a future video.